Hello, everybody. Today, we're going to dive into some of the concepts that we've been talking about, but we're going to go into a little bit more depth. We're going to cover the integration by parts formula. We already covered a lot of examples. Today, we're going to dive into some more complicated examples. So let me share my screen real quick. And as usual, if you have any questions, feel free to drop them in the chat. Otherwise, we'll just continue kind of where we left off as normal. So just as a brief refresher, yesterday we talked about the integration by parts formula, right? Or this technique of integration, which is really the opposite of the product rule. It's more complicated than some of the other techniques that we've seen, but it is still the opposite of a derivative rule you already believe. So that's the good news. And we basically learned that we have this formula. This formula right here is the integration by parts formula. I won't go through everything. And we also talked about some general rules for how to choose U. And then we walked through a couple examples, right? So I won't, like I said, I won't rehash everything, but we walked through, I think, 2 examples. Yeah. And today we're just going to continue with some more complicated examples. So here, remember, this is the magic formula that we're going to use to solve all these. And now let me come up with something to try. We already tried. So we tried the case of where we have like x cosine of x. We also tried x squared cosine of x. So those basically the x squared one. Remember, we needed to use 2 rounds of integration by parts. Here, let's do a little bit of a more complicated one. How would you solve? Think about how you would use integration by parts to solve this. So if I have like integral, and then let's actually say cosine x times e to the x. This is something we can't solve. We couldn't really solve this before. There's no method that allowed us to solve this. But with integration by parts, we actually can. So go ahead and take a couple minutes and see if you can think about how to solve that. Feel free, if you're watching the recording, feel free to pause the video. But yeah, coming back to this, if you're not sure how to do this, think about it like this. And first, let me actually if I grab our guidelines for how to choose U, this problem that we're looking at right now is actually kind of hard, or compared to the other ones at least, because this breaks down. Remember, normally rule number 1 works like 95% of the time. Right now, we're in the 5% of the time. So if you think about it, they're like neither of these. You can't, if you choose this as U or this as U, and you just keep taking the derivative of them, there's no way that either of them will ever become a constant, right? So there is no value we can choose that will eventually become a constant if we take enough derivatives. So rule number 1 kind of fails here. Like I said, the vast majority of the time it works. Here it fails. So what else can we do? The only other option, so like we have to pick something. I will say that integration by parts works here, but it works in a strange way. Basically, this is kind of ironic, but it doesn't actually matter which one you pick as U. I'll just pick this one as U, just because I think it'll be slightly easier. Well, actually, they're basically the same. So yeah, let's do that. If you did this problem, and if you want, I'd encourage you, like I said, if you're watching the recording, if you want, try doing the problem that we're about to do with the opposite choice of U. It'll still work, or it should still work if you do everything right. So if I choose U as e to the x, and I choose everything that's left as dv. Again, now we do just the normal technique. So du is equal to derivative of that times dx. And then integral of this is sine of x. So that's normal. And remember, now we need to use the formula here. So uv, let's copy this down. Uv is what we copy in. Uv minus that. What would that be in this case? Well, you just kind of copy it in. Let's see, that'll be e to the x times sine of x minus the integral of basically v, which is sine of x, times e to the x dx. All right, because e to the x dx is du in addition to being u. So if we do 1 round of integration by parts, we get this. And if you think about it, it seems like it doesn't really help with anything, right? And it kind of looks like it doesn't. But there's actually, this is going to turn out differently than it normally does. But this actually, I'm just simplifying this down. So basically we end up, whoops, too much. With this integral equals this. And actually, this this is actually doable now because this is the equal sign. So, like I said, it seems like we replaced. It seems like we made things worse when you look at it like this, right? So it's like if we start off with this, and now we ended up with something just as hard as that, plus a bunch of other stuff, or minus a bunch of other stuff. So what do we actually do there? The trick is do another round of integration by parts. So here, and again, the beauty of it is it doesn't matter which one you pick actually. So here, let's say I'll pick u equals e to the x again, and then I'll say dv is the other portion, sine of x dx. And then if we're doing another round here, du is equal to e to the x dx. And then v is equal to negative cosine of x, right? So if you take the derivative of cosine as negative sine, the derivative of negative cosine as positive sine. So the antiderivative of sine is negative cosine. Hopefully that makes sense. And then just let's do another round, right, with the formula. So it'll be, we'll have this negative on the outside. Think of it like this, where we have these braces, kind of like we did last time. We've done problems, or we've done one problem where we do 2 rounds of integration by parts. Here we're doing 1 round. So here uv, what will that be? That'll be e to the x times negative cosine of x minus the integral of basically v, so again, negative cosine of x, and then times du, which will be e to the x dx, all inside of here. And now, if you think about it, like again, it looks like we're just making things worse and worse, right? But I promise we're not. All right, let me simplify this. So here, if we're looking at this, hopefully it makes sense that we're now going to end up in this position where we have, basically where we have this so far, but we're still in trouble, right? Because the thing we're starting with is just as hard as, like, the thing we're ending with is just as hard as what we're starting with. It's not slightly hard because of the negative. So again, it looks like we're making no progress. And these are weird ones, by the way. This is a very unusual case, but it does happen. Anytime you're dealing with a function that never becomes a constant, this might be a way to solve it. Basically, so, and I'll just get even more specific. Anytime you're multiplying sine or cosine by some exponential, this technique we're using now will work. But basically, you do it twice, and you'll see it work out. But here it's kind of complicated. I'm just going to simplify this down a little bit. So this is going to be negative e to the x cosine of x. And then I'm going to bring this negative out. So plus the integral e to the x sine of x, or sorry, cosine of x dx. All right, just bringing this negative out. So negative times a negative is a positive. And then we still have this on the outside. So we still have all this stuff, right? And then what I would do is I would distribute the negative through again. I would distribute the negative through again through these purple brackets. And you have to be really careful on these, like as you'll have multiple rounds of like brackets, and you have to make sure you don't get confused by your own brackets. That's actually kind of a big problem on these sorts of problems. But we get, let's see, e to the x cosine of x, and now it'll be minus the integral of e to the x cosine of x dx. And here, like I said, it looks like we're ending up with the same integral we started with, but we can actually deal with that in a clever way. Think about it like this. This whole integral is a number or a function or some type of expression. So let's just mark it S for, some expression. And then let's think about this. We would get what? S equals all of this. So all of this, except instead of having this whole thing, this would just be some constant. So this would just be some constant minus S. And think of S, you can think of S like, X we're already using, but just think of it like some variable. How would you solve? So basically there's a recurrence definition, if that makes sense. So like the actual thing we're trying to find, this integral, the answer is in terms of itself. Like the answer has itself in the answer. So that's like what's called a recurrence relation typically. You don't have to get caught up on that. That might be like overly complicated language. But basically, you have to do this. So how would you do this? How would you solve for S? Basically, you just add it to both sides, so you get 2 times S, right? Equals that, and then you just divide by 2 to solve for s. So s would have to equal 1/2 of all this stuff. So 1/2 e to the x sine of x plus 1/2 e to the x cosine of x. And then don't forget your plus c here. So when we solve that. So remember, what was s? S was really just a shortcut. It was basically what we just called this entire integral. We just called this entire integral like s. So that is basically what we did there. So there you go. That is the answer. That's how we integrate that. So to summarize, it's like if you basically neither of these, so remember our typical rule breaks down, the thing that usually works breaks down here. If we keep taking the derivative of either of these, if we set either of these equal to u, they will never equal a constant when we keep taking the derivative. So we just pick one, basically, pick one or the other. And then what we do is we essentially grab or we essentially work through this problem. We get an answer in terms of what we started with, but then we can kind of we look at it as a recurrence formula or a recurrence relation, and then we can kind of solve it from there. We can basically cleverly put it on the same side, divide, and get our answer. So here, everybody, I have to do something real quick, but just give that a try, I'll say. So give that a try, and then I'll respond, or I'll come back and we can check to confirm that it's right. But just give it a try on your own. Maybe take a couple, like a minute or two, and then I'll come back and we can try that. But basically, double check, like think about how you check if this actually is the answer. Cool. So now think about was anybody if you're able to figure that out, feel free to just drop it in the chat, or comment below this post if you're watching it afterwards. But otherwise, we'll kind of go through here. Remember how we actually check this? We basically, if what we found really is the correct antiderivative, basically, if we take the derivative of it, we should get what we started with. So let's see if that actually happens. So here, if this is our answer, if this is what we're saying the answer is, and we take the derivative of this, then what would we get? So basically, we would get 1/2, and then think about this. This is essentially the product rule, right? So derivative of the first is also e to the x, and I'll factor out the 1/2 here. But derivative of the first, leave the second, right? Plus, leave the first derivative of the second, so plus e to the x cosine of x. So hopefully that makes sense. That's the derivative of this first portion. And then let's think about what's with the second portion here. So with this, we get plus, again, you can factor out the 1/2, and you basically have to do another product rule. The derivative of the constant is just going to be 0, obviously. But how do we do this? Derivative of the first, e to the x, leave the second, right? And then plus, leave the first, we're just doing a product rule here, leave the first, and now derivative of the second, negative sine of x. That is the derivative. And the question is that what we started with? Well, let's see. Let's work this out. If we simplify it, 1/2 e to the x sine of x plus 1/2 e to the x cosine of x plus 1/2 e to the x cosine of x minus 1/2 e to the x sine of x. Well, if you think about it, we have 1/2 e to the x sine of x minus 1/2 e to the x sine of x. So those cancel out, and then we have basically the same thing, just 1/2 of that thing plus another half of that thing. That's just one of that thing. Or in other words, e to the x cosine of x. That is what we started with. So that's right. So that's how we can prove that this derivative, this answer, this antiderivative is the true antiderivative of what we started with. How do we know that? Because we took the derivative of it and we got what we started with. So There you go. This is a more complicated integration by parts problem. Hopefully that makes sense. And then here again, there are some like really complicated integration by parts problems. If you come across them in your class, of course, just post about them in Skool, and I can like answer them for those. I can answer them for those specific cases. But otherwise, what I'll do is I'll just I won't go again. It could get harder than this, but if you get everything we've done so far and the next one I'm about to show you, you'll get like 90% of the different scenarios they can throw at you. So basically, looking at this, actually, let me come up with another one here. So let's say x to the seventh times cosine of x. So give this a shot, or actually don't give this a shot. Just look at it and get overwhelmed by it. That's probably better. Don't actually try to do the work yet because there's a faster way. But the big thing you'll notice, if we try to do our normal technique, right? Normally you'd say which one becomes a constant the fastest if we keep taking the derivative. Is it x to the seventh or cosine of x? Cosine of x will never become a constant, no matter how many times you take the derivative. X to the seventh will. The problem is you have to do it 7 times. You have to take the derivative 7 times, which is kind of a lot. Like we've done like the last 2 problems we did today and yesterday, we did 2 rounds of integration by parts. Imagine if we did 7. That would be a lot more work, right? And you probably don't want to do that. So you would have essentially 7 integration by parts problems inside of themselves, which is, like I said, that's a lot. So what can we do instead? Basically, see if this makes sense. What's the normal integration by parts formula? Let's grab that to start. So here, let's say, so this is the normal integration by parts formula. So we'll come back to this problem in a second. But basically what I'm getting at is an additional technique called tabular integration. So tabular, and you'll see why it's called that. Tabular integration. So tabular integration, it's basically it's integration by parts, but with a table. So that's what the tabular part means. It's like table. Now you probably don't understand what that is yet. Let's go into that. So if we have like u or v or sorry u dv, so u dv is equal to the integral of uv. Let's think about this. So the first step we do when we're trying to solve this integral is we integrate the v. Okay, so we integrate the v. We don't do anything to the u in the first term. And then in this term, think about what we can do. I'm gonna use like kind of an ugly notation here, but see if this makes sense. Inside of these brackets, think about it. Inside of these brackets, what do we have? We basically have, we can do another round essentially. So what do we do every time? So first off, like look at this. Think of it like this. Think of it v. Think of dv as v dx. So as the v here, which is kind of a weird way of wording it. But then what would the v equal? Well, you just integrate that, right? So I'm just going to write the integral of v. Again, this is going to be an ugly notation, but this will help you. This should help you get the idea. So I'll kind of put right in this. And then u is actually du. And what we normally think of du is actually the second derivative. I'll just write it as like d squared u. Like I said, this is going to be ugly notation, but I just want you to get the basic idea. And then if without like kind of getting bogged down with the uglier notation, what would happen if we did the rules again? Well, here, think about it. It would be the integral of v times the derivative of the original u, right? Minus the integral of integral v, right? And then the second derivative of u, d squared u. So this is kind of getting a little complex, but hopefully that makes sense. And then what you can do at this point is you can break this down, right? So if we break this down, what do we do? Basically, I'll just do one more round so you don't have to get too carried away with this. But basically, again, it's like the normal thing. Instead of like actually, I'll do this one more time. So what we normally think of as u, this case would be d squared u, the second derivative of u. So d squared u. Like I said, I'm being a little lazy with this notation. There's no real clean way to write it. And this would be the third derivative. So the third derivative of u. And then if you think of this, so what would dv equal? So dv, that would equal the integral of v, right? And then what would the v equal? That would be like, I'll just say the double integral or the second antiderivative. You just integrate it twice, basically. And then if we use the normal pattern, uv, so it'll be like right here, it'll be the second integral of v, the second derivative of u, right? Minus, and then you just kind of do another round. So if you do another round here, then it'll basically be, I'll say minus the integral, and then again, you don't have to get caught up with this, but second integral of the original v, and then it'll be like the third integral, right? And you would just continue like that forever, like, right? If or for however many rounds you need. We have set, like in our problem below, we have 7. We would have to do this 7 times. I'm just doing it a little abstractly so that we can notice a pattern. And then here, I think we probably have enough at this point to have the pattern. So what would this be? So the integral of u dv, like the original problem we're trying to solve, what would that equal? You basically bring down the uv. So we have uv, and then we have minus. So think about it. We're going to distribute one negative sign here, minus what's going to be the integral of v times the derivative of u. And then we're going to distribute this negative here, right? And think about what this is going to be underneath. It's going to be like we still have this negative on the outside, and we still have this right there. So that's going to become a negative. But then if you distribute a negative to this negative, you're actually going to get a positive. And what's that positive? That's going to be the second derivative, or the second integral, sorry, of the function you keep integrating, in the second derivative of the function. And then what's happening after that? Here, it'll be like, it's kind of complicated. You distribute one negative sign to make that positive, and then you distribute another one to make it negative again. So it's going to be negative, and like we're going to continue with the pattern like this. So when you look at it like this, when you actually like try to use the integration by parts formula repeatedly, that's the difference. We're doing it over and over and over again. Like we've done it 3 times so far. We could do it 4, 5, 6. We could keep going like this forever. Hopefully you can see there's a clear pattern that emerges. Whatever your original, like basically you take an original thing to differentiate, an original thing to integrate. And then basically the first thing is you just, like rule number 1 is you just integrate the first thing by hand. You just integrate the first thing. So like the dv becomes v. The v is the integral of dv. And then after that, what's happening? We alternate the signs for every term, and then the thing we keep taking the derivative of, we just keep taking the derivative of it. We just take another derivative, right? And then the thing we keep integrating, we just keep taking another integral. And you just continue like that. That's arguably, if you get this process, this is arguably a simpler pattern than using the actual integration by parts formula. So how would we apply that here? Why is this such a big deal to like understand how this works? Because if we understand this process, we can just do the same thing with a table of values. We don't have to actually do it. So here's how you would do tabular integration. You still choose u and v the same way. So you say u is x to the 7th, and then you say dv is still cosine of x dx. Or I'll just say cosine of x here. But then here's the difference. You then create a table. That's why it's called tabular integration. And you do plus, minus, right? And you just keep alternating on the way down. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. And you just keep going until you'll see how far you have to go. And then here's the important detail. You put u in the starting spot, so x to the 7th, but then you do not put dv in the starting spot. You actually take the integral of it. Because remember, like in the formula, on the first term, we're not touching u. We're taking the integral of v without touching u. That's the important detail. So that means you have to take an extra integral of the dv at the very beginning, and then from there, then they're going to be synced up. So you have to remember to integrate this. So you would actually put v in there, which in this case would be sine of x. So hopefully that makes sense. And now this is kind of a much simpler process once we get the mechanics. So we basically found our first term here. Positive u, x to the 7th times v. The first term is going to be plus x to the 7th times sine of x. And then the second term will be minus the integral of this thing. We're going to keep taking the integral of the v, and we're going to keep taking the derivative of this column. So basically, you can this is kind of like mass production, or like batching, if you will, like doing the same thing over and over for integration by parts, which makes it simpler. You just get your brain primed to like take the derivative, and then we just blast through it. Let's take the derivative like 6 times in a row. 6x or 7x to the 6th, 42x to the 5th, 210 x to the fourth. 440 x to the third. 1200, 120. So I guess 1320. So 1320 x to the second. And then I guess 2640. Stop when you hit a constant. You're taking the integral of it. So what's the integral of sine of x? Negative cosine of x. Integral of that, negative sine of x. Integral of that, positive cosine of x. Integral of that, positive sine of x. And after we do, for sine and cosine, after you do 4, you should always end up back where you started. And then repeat the process, basically. Negative cosine of x, negative sine of x, positive cosine of x. So this is simpler because we're just taking the derivative down this whole column all at once. And then we're taking the integral down this column all at once. We're not like switching back and forth, which we would have to do with the normal formula. And then basically here's the idea. Every single one of these is a term. So that, just multiply them all together and those become the terms here. So the answer here is actually x to the 7 sine of x, positive. And then here, it's actually, there's going to be minus minus, so it's actually going to be positive again. So plus 7x to the 6th cosine of x. That's the second term. And then the third term is going to be minus 42 x to the 5th sine of x, right? And then you can see how this is going. So like, then what would it be? Negative 210 x to the 4th cosine of x plus 440 x cubed times sine of x, and minus minus plus 1320 x squared cosine of x minus 2640 x sine of x. Hopefully you can see the value in this. We're basically avoiding a massive amount of work here. And then you can say plus c finally at the end. That's the answer to this one, assuming we did everything right. After I finished recording, I noticed there was a small algebra error, but it threw some of these off. So here, this is the actual answer. So basically, the issue was taking the derivative, like starting between here and here. So if we bring the 4 down, I was multiplying, I think I multiplied 2 by 2 to get 4. I should have done 2 times 4 to get 8. So that should have been 840. So this number should be 840 right here. So 840. And then basically continuing, like, so 840 times 3, 3 times 8 is 2,400. 3 times 40 is 120. So 2,400 plus 120 is 2,520. So that should be right here. That should be 2,520. 2,520, and that's going to throw that off. And then you can see kind of how they fix it. Then you just double it. So 2,500 times 2, 2,500 times 2 is 5,000. And then 2 times 20 is 40, so 5,040. That's where that comes from. So these two should be 5,040. So that'll throw these off. So minor correction there. Apologies for that. Is one, you can see how this is a good lesson actually, and how easily one mistake can throw things off, right? If you just make one tiny mistake there, even I did, like, given that this was wrong, I did these 3 right, but because that was wrong, it threw those off. So you got to be very careful about that, especially when you're doing any derivatives or integrals, but especially tabular. You have to pay special attention to that and always double or triple check. So hopefully that makes sense. But yeah, apologies for that. Apologies for that mistake. So there you go. We basically just did, because we understand how this pattern works, we can create a table and we can kind of think of it like an assembly line for integration by parts. It allows you to do integration by parts repeatedly, like one after the other, a lot. So that basically allows us to, like, we just did the equivalent of 7 rounds of integration by parts. Like, this would have been very painful if you tried to do that, but this is the alternative. So there you go. That technique is called tabular integration. To be honest, you can use tabular integration even if you're only doing it once or twice. You can do that. In fact, it might be easy. You might find it easier. The only situation where you can't use tabular, and like I would almost say, like, for some of you, like, maybe you'll find it easier to just never use the integration by parts formula and just always use tabular. Even if you only have to do it 1 time or 2 times, it's like, it's better to get in the habit of that. The only time I would say that it won't work is kind of the last problem that we did, where we get to the point where it's like we have a recursive answer. That's the only time where tabular won't work, at least the normal way. You can kind of recover from it if you know to look out for that. But in general, like aside from that case, tabular integration works. It definitely works more efficiently if you need to do 7 rounds of integration by parts. And I would argue it also works more efficiently if you have to do 1 or 2. If you know, as long as you know how to think about it. So this is an alternative method. Like I said, it's really just a more optimized version of integration by parts, but that's how you do it. And that's how you set it up. And that's why tabular integration behaves the way that it does. It's really just, we do the integration by parts formula inside of itself over and over, and we kind of notice this pattern that pops out. So there you go. Hope that makes sense. Just let me know if you have any questions. Feel free to drop your comments below this post in the Skool community for the recording or on the YouTube video. But yeah, other than that, hope that helps and have a great day.